Okay, welcome back. In this video, we're going to talk about how long this radioactive substance can stay around. How long is it going to be on the Earth and causing radiation and being dangerous? And so this is kind of an interesting topic today. But I wanted to start off with this slide right here and talk about it for just a second. If we look at it, what it says, it's the nuclear decay of uranium-238. So uranium is radioactive. The nucleus is too unstable. If you look at it on the periodic table, it's got 92 protons. Its atomic number is 92. That's a lot of protons in a small space. They want to repel. It makes it unstable. It gives off radiation until it becomes who, guys? What's the largest stable atom on the periodic table?
Lead.
Lead. Thank you, Dallas. So 82. Everything above 82 wants to give off radiation and decay until it becomes lead. So that's kind of what this diagram right here is showing us. We're going to start with uranium-238. Now, here's the key. If you see a downward arrow like this, it means it loses. What particle is that, guys?
Alpha.
That's an alpha particle. So it loses 2 protons, 2 neutrons. Okay, if you see a little tiny arrow to the right, that's the loss of this particle. What is it?
Beta.
That's a beta particle. So that's kind of the key here. So let's look at what happens to uranium-238. It lost a what right there?
Alpha.
Alpha particle. It became thorium. If you look on the periodic table, uranium is 92, thorium is 90. So it lost 2 protons. It became smaller. Well, then it gave off what? A beta. What again? A beta. Then it lost what? An alpha particle. An alpha particle again and again and again and again. Every time it loses an alpha particle, you lose 2 protons. So it becomes smaller by 2 elements on the periodic table. Okay? Then it goes beta, beta, then another alpha particle, until it's become who? Lead. Well, it has to give off all of that radiation. So look how many steps there were there until it becomes stable. So that's just, one element, uranium-238. The question that we're going to focus on in this video is how long does this process take? How long would all of this take? It's measured, chemists measure it in something called a half-life. And a half-life is the amount of time it takes for half of the substance to decay. So even though half of it's decayed, you still do have half of it. So half-life is kind of a funny way to measure it, but that's how they do it. So let's look at it. What's the half-life of uranium-238, guys? Times 10 to the 9th years. That's 4.5 billion years. And then, so after 4.5 billion years, you still have half of it. So how long really is uranium-238 going to be around? Forever, right? It's going to be around forever. 4.9 billion years just is the amount of time it takes for half of it to decay. Okay, well, it became thorium right here. What's thorium's half-life? Only 24.5 days. So look at the drastic changes in these half-lives here. Uranium-238 was in the billions of years. This one's in days. Okay, if you scan through this one's in minutes. There's even some to like 10 to the minus 4th seconds. Some don't stick around very, very long at all. So that's kind of what the danger is with dealing with nuclear power plants. It produces nuclear waste, which can be around for a long time. And that's what we're going to focus on in this video. Okay, so hopefully that gives you a little bit of an idea of what we're talking about. Okay, half-life and radioactive dating. Before we get into calculating half-life, let's talk about this thing right here, radioactive dating. You might have heard about this. This is how chemists can figure out how old different objects are. In fact, that's how they figured out how old the Earth is. The oldest rock on Earth has been radiometrically dated to 4.5 billion years. So that's how long they know that the Earth has been here for. Okay, so let's write this down. Half-life. I think in your book you're supposed to write down the definition for half-life. Correct? The half-life of a substance is the time it takes for half of the atoms of a radioactive substance to decay into a stable isotope. So it's the time it takes for half of the atoms to decay into a stable isotope. So just remember, even after that time, you still have half of it remaining, right? So that's what a half-life is. Here's an example of how they use radioactive dating. Say you have carbon-14. It's radioactive. Its half-life is 5,730 years. There's a diagram down here kind of explains how they do radioactive dating. All plant life, this is a log, so it was a tree when it was alive, takes in carbon in the form of CO2 from the air. Well, we know that carbon-14 has a certain percent abundance. We know what that is. And so chemists use that to figure out how much radioactivity is given off. If it's given off 100% of it, that means all of the carbon-14 was still in that tree at that time. And so we would know that its age is 0. Well, what if only 50% of the radiation is being given off that it should be? Well, then we know it's gone through one half-life, because what's half of 100%, guys? 50%. So it's gone through one half-life, and we know that the half-life is 5,730 years. So you could date that log, right? What if only 25%? How many half-lives did it go through now? 2 half-lives. So we take 5,730 times it by 2, and we know it'd be 11,460 years. Well, what if only 12.5% of the radiation is being given off from that log now? Then it's 17,000 years. And that's how they use radioactive dating to date things. So that's one of the real life benefits of radioactivity. Okay, here's a radioactive decay graph. I want you to focus on how much we have here, guys. What do we start with? 10 grams. What's half of 10 grams? Well, 5 grams. How long did it take to go from 10 grams, right here, this would be so down here is time 0, we have 10 grams. How long did it take to go to 5 grams? 1. So that's 1 half-life. That's half of it. Another half-life would get you to how many grams? 2.5 grams, because take 5 divided by 2 is 2.5. And another half-life. So that's what we're going to be doing, is making and being able to interpret graphs like this. Yeah. The half-life is determined by how many years it takes for half of the atoms to decay. So we just look at the amount of time it takes for half of it to be gone, and that's your half-life. Okay, it could also be shown as a percentage. So if we start with 100%, what's half of 100%? 50. How long did it take to get to 50%? Well, 1 half-life. The next half-life, so 2 half-lives, you get 25. Then you just keep taking half of this number here and get to the next half-life. All right, solving half-life problems. We're going to talk a lot about this in this video. I've got a good system that works, and if you follow it, I promise it will work every time. And some of these are going to be easy and you think you can do them in your head, but I caution you on that. Please write it out. Please do it this way, at least at the beginning, and I promise you're going to make less errors. So it says a 100-gram radioactive substance has the half-life of 10 years. How many grams of this thing will be left after 30 years? So, even though this is not in your book, I want you watching up here. We always write down what they give us first. So 100 grams. Okay? It says it has a half-life of 10 years. Here's how I represent a half-life. I represent a half-life with an arrow, and I put a number 1 under it, because that's the first half-life. I put how long the half-life takes above it. How long does a half-life take in this case? 10 years. Thank you, Zach. 10 years. After one half-life, how much is going to be left? Half of it, right? 50 grams. Okay. Well, it said how many grams are left after 30 years. So that's only after 10 years, 50 grams will be left. So what do I got to do? Yeah, let's go another half-life. I'm going to put a 2 under it because that's the second half-life. Again, how long is a half-life? 10 years. That doesn't change. So after that second half-life, how much is going to remain? 25 grams of that substance. Well, that's only how many years? 20. I've got to go to 30 years. So let's do another half-life. How do I represent a half-life? With an arrow. Put a number 3 under it because that's our third one. How many years is a half-life? 10 years. Okay. What's half of 25? 12.5 grams will remain. And how many years has that been now? 30 years. So there's your answer. After 30 years, you'll have 12.5 grams of it remaining. So I promise if you'll just represent a half-life with an arrow, put the number of half-lives underneath it, put the length of the half-life above it, these questions will make a lot more sense to you. Okay, so that's kind of what we did right there. There is a way to solve this mathematically, but we're not going to get into it in this first year chemistry class. It can get into logarithms, and a lot of you aren't familiar with that yet. So we do that in advanced chemistry, though. Okay, I've got a lot of practice problems coming up, so please stay with me. If you're watching the video, pause the video, see if you can answer these practice problems on your own, and then once you have an answer, hit play and see if you get it right. So here we go. Practice problem 11. It says, what's the half-life of a substance shown below? Okay, how much did we start with, guys? When you're looking at a graph, it's always important to read the axes. What's measured on this y-axis?
Mass.
The mass of the substance in grams. What's measured on the x-axis? Time in years. So at least we know what it's reporting, right? Okay, how much did we start with at time 0? 400 grams. Okay? Well, it wants to know what is the half-life of that substance. So what's half of 400 grams? 200. Well, how long did it take to get to decay down to 200 grams? You look down here, that amount of time took 5 years. So there's your half-life. Sometimes you'll see chemists write T to the 1/2 like this. That's kind of how they write half-life. So the half-life is 5 years. Okay, good job. Let's see if you guys can do 12. Again, it says, what's the half-life of that substance shown below? Okay, what'd you guys get?
2 years.
Good. Well, we're starting with 400 grams. To go to 200 grams, how long did that take to go to half of it? It took 2 what? 2 seconds. So the half-life here is equal to 2 seconds. Yeah, always look at your units. This time it was measured in seconds. Oh, then it says also, how many grams will remain after 4 seconds? So if the half-life is 2 seconds, in another 2 seconds, how much is going to remain? 100, because we just take half of 200, that's 100. And so we could fill in that graph. It's going to look something like this. So after 4 seconds, we're going to have how much? 100 grams? Okay. What about after 8 seconds? Okay, well, let's do it one half-life at a time. A half-life is 2 seconds, so another 2 seconds, how much is going to remain? 50. Okay. So again, this was 200 grams, so half that's 100. This would be 50 grams. So at 8 seconds, how much is going to remain?
25.
Yeah, it's just going to be 25 grams. So after 8 seconds, 25 grams. Okay, good job. So let's go to practice problem number 13. It says, if we start with 400 atoms of radioactive substance, how many atoms will remain after one half-life? So I want you to write it down like this, 400 atoms. Okay, how do we represent a half-life? An arrow. Okay, this is the first one. So after one half-life, how much is going to remain? 200 atoms. This is half of it. After two half-lives, how much remains? 100 atoms. Okay. It wants even 3 half-lives. How much is going to remain? 50 atoms. So there we go. So 200, 100, and then 50. Good job. Let's see if you guys can solve this one. If you're watching the video, hit pause on your video and try to solve it, and then hit play and see if you got it right. So let's give you some time to work this one. Okay, so let's see if you set it up correctly. Here it says we start with 16 grams. I always like to underline what we start with. And then it says how much will remain after 3 half-lives. So we want to go 3 half-lives. So we're going to write 16 grams. Remember, an arrow represents the half-life. I'm going to put 1 for the first half-life. How much will remain after 1 half-life, guys? 8 grams. Okay. After 2 half-lives, how much is going to remain? 4 grams. And finally, after the third half-life, 2 grams. Okay. So there's your answer. How many of you guys got that right? Okay, good job. Okay, let's, and that was the answer, 2 grams. Good job. Okay, number 15. Now we're going to change it up a little bit. We're not talking about grams anymore. We're starting with a percentage. And so let me go through this one with you. It says a radioactive substance has the half-life of 10,000 years. So there's some information we're going to have to use. Half-life is 10,000 years. And then it says only 25% of the original sample remains. And then it really wants to know how old. How old is this radioactive material? So instead of starting with grams, what are we going to start with here, guys? What's the biggest percentage you can start with? 100%. So that's what we're starting with. After, now an arrow represents the half-life. This is the first one. How long was this half-life? It told us actually. 10,000 years. So I'm going to put 10,000 years on top. So after one half-life, what percentage will remain?
50%.
50, yeah. Half of 100 is 50. So 50% remains. Well, it said if only 25% of the original sample remains. So can I stop there? Nope. Let's go again. Another half-life, so I'm going to put a 2 down there. It's still, does the half-life ever change, guys, for a substance? No. It's always the same for that particular isotope. So another 10,000 years. How much are we going to have? What's half of 50? 25 what? Percent. Okay. So now we have only 25% remaining. How old is that radioactive material?
10,000 years.
Yes, and then we add up the half-lives. 10,000 plus 10,000. Whoa. Okay. Yeah. 20,000 years. How many of you guys got that right? Good job. Okay, 20,000 years old. Okay, number 16, let's try this one. It says, what's the half-life of a 100-gram sample of nitrogen-16 that decays to 12.5 grams of nitrogen-16 in 21.6 seconds? This is also asking us a little bit different question. It's saying, what is the half-life? So I'm going to go through this one with you. Okay. What are we going to start with, though? How much are we starting with? 100 grams. So put 100 grams there. And it says it decays all the way to 12.5 grams. Can we figure out how many half-lives that is? Sure. Let's do it. So arrow, number 1. How much remains after one half-life? 50 grams. And arrow, number 2, how much remains? 25 grams. Another arrow, number 3, how much remains? 12.5 grams. Okay, now how many half-lives did we have to go through?
3.
We had to go through 3 half-lives. Okay. How long did this whole process take? 21.6 seconds. That's how long it took from 100 grams clear to 12.5 grams. So if that whole process took 21.6 seconds, how could we find out how long each half-life is? Good, Zach. Yeah. So we'd take the total time, which was 21.6 seconds. Let's divide it by the number of half-lives, and that will give us how long each half-life must have been. Okay. So 21.6 divided by 3. Are you guys getting 7.2? 7.2 what? Seconds. Good job, Dallas. So each one of these, and we can go back and check ourselves by doing this. 7.2 seconds. 7.2, 7.2 seconds. If you added all these up, would it be 21.6? Yeah. And so the half-life of that substance must have been 7.2 seconds. Good job. And we got it right. Okay, number 17. I'm going to give you a second and try it. Okay? So use the same method that I've been using, and I think it will work for you. So I'm going to pause the video and see if we can give you some time to work. Okay, let's go through this problem. It says all isotopes of tactinium are radioactive, but they have widely varying half-lives. If an 800-gram sample of tactinium-99 decays to 100 grams in 639,000 years, what is its half-life? Okay, a couple of things as we read this. I always like to underline the information that they give us. We're starting with 800 grams, and we're decaying to what? 100 grams. So let's underline that. And it said this whole process, going from 800 to 100, took how long? 639,000 years. And it wants to know what we're supposed to solve for is how long one half-life would be. Okay, so like the previous problems, what do we start with? Yeah, we start with the mass, 800 grams. It decays to how many grams? 100. So let's show how many half-lives that would take. After one half-life, how much remains? 400 grams. After two half-life, how much remains? 200 grams. Can I stop there? Nope. We need another half-life. How much remains after that one? 100 grams. Can I stop there? Yes, because that's what it said it decayed to. Okay, so we've got 3 half-lives. Well, it also said this whole process, going from 800 all the way to decaying to 100 grams, took how long? 639,000 years. But pay close attention, it says, what is its half-life? So we want one half-life. How do we get it? Good, we take the total time and divide it by how many half-lives we had? 1, 2, and 3. Okay, so let's take 639,000 divided by 3. Are you guys getting 213,000? Okay, so it's equal to 213,000. 213,000 what? Seconds, minutes, weeks, years. Yeah, how do we know it was years? Because that's what they measured the total time in. Years. Okay, and that's your answer, but if you ever wanted to check yourself and see if you did it right, you could put 213,000 on each one, above each one of these arrows. And if you added all three of these guys up, it would add up to the total time. So that is the half-life of Tectinium-99, 213,000 years. Okay, very good. I think I've got a couple more practice problems coming up. So we're almost done. Okay, practice problem number 18. What is the half-life of the substance below?
20 years.
So, okay, good. We're starting with 800 grams. How long did it take to go to 400 grams? 20 years. So that'd be 20 years. Half-life is 20 years. Okay, so. Oh, and then I wrote right over that one. Okay, it says, how many grams will remain after 100 years? Can we figure this out, guys? Let's just keep going here. Okay. Let me rewrite that. The half-life of this substance was what? 20 years. So every 20 years, it decreases by half. So let's do another 20 years. What's it going to be at 40 years? How many, guys? Oh, no. Yeah, it's going to be 200. I'm going to make note of that. 200 grams right here. Let's try our best to make the graph follow there. So, but it wanted to know how many grams will remain after 100 years. Okay, so what are we going to do next? What's 20 more years farther than 40? What are we going to be at? 60. How much is going to remain? 100 grams. Okay, so that graph is just kind of coming down. And then 20 more years is what? 80. How much remains at 80? 50 grams. Okay, so this kind of keeps coming down. I didn't really draw the curve very good, did I? Can we stop there? Nope. Let's go another 20 years, so another half-life, 100. How much is going to remain? 25 grams. That would be your answer. Okay, so the half-life was 20 years. That's the half-life. And how much remains at 100 will be 25 grams. Good job. Okay, number 19. Let's see if you guys can do this one. I'm going to pause it again. So if you're watching the video, pause it. See if you can get this last practice problem. Okay, let's see if we can solve it. So it says the half-life of potassium-42 is 12.4 hours. How much of a 750-gram sample is left after 62 hours? All right, this is a little bit different question here, so let me help you through it. Let's underline what they give us, okay? Half-life equals how many hours? 12.4 hours. So one half-life takes 12.4 hours. How much of this 750-gram sample, so that's what we're going to start with, is left after 62 hours? So, what do we got to figure out here first, guys? Good, Abby. How many half-lives do we have to go through? Okay, there's a couple ways you can do this, but maybe the easiest is to just start here with 750 grams Okay, this half-life, the first one, how long does it take? 12.4 hours. Okay, I need to go until we're to a total of 62 hours. How could I easily determine that? Good. Let's take 62, the total time, and divide it by one half-life, which was 12.4. And what does that equal, guys? Do it on your calculator.
5.
Good. So 62 divided by 12.4 equals exactly 5. So what did that tell you? 5 what? That's how many half-lives we have to go through. Okay, so let's go through 5 of them. So after one half-life, what's half of 750? 375 grams remain. Okay, we have to go through 5 of these guys, so let's keep going. After the second half-life, which was 12.4 hours again, how much remains?
187.5.
Good, 187.5 grams. Okay, let's keep going. I got to go up to 5 again. 3 half-lives, another 12.4 hours went by. How much remains? 93.75. Okay, another half-life. 12.4 hours go by. How much remains?
46.
Good. 46.875. Okay, one more, so the fifth half-life. Another 12.4 hours go by. How much remains?
23.4.
Good. Let's round it to 2 decimal places. So 23 point what? 44. And we're measuring in what?
Grams.
Grams. Okay. So that's how much will remain after 62 hours. If you wanted to check yourself, you could really add all these half-lives up, and if it adds up to 62, you've done it correctly. Does that make sense? Okay, that's my last practice problem for half-lives, and that's how you calculate half-lives. Hopefully that makes these problems a little easier. I promise you, if you'll just write the arrows for the half-lives, number them underneath, and put the time for the half-life above it, it makes it a lot easier. And so, okay, we've learned enough to do a worksheet in the student workbook. The worksheet that I would like you to work on is called the half-life worksheet. So let's stop here and complete the half-life worksheet.